Hello, Chem 1B. This is Chapter 21, Lecture Video 1, and we're going to be talking about organic chemistry for the next chapter, which is a very important field, especially for anybody concerned with medicine of any type. You want to be a vet, you want to be a doctor, you want to be a pharmacist. OChem, as it's commonly known, is going to be vital to your future career. Let's talk about organic chemistry. Organic chemistry, what is it? Organic chemistry is the study of carbon-containing compounds, primarily. That's a bit of a broad definition, but it works. Why is carbon so special? Why do we have to study carbon? Why is that so important? Well, other than the fact that most life on planet Earth is carbon-based, it's unique in a number of different ways. One, it forms so many different compounds. There are hundreds of thousands of different compounds that carbon can make, and each one has different properties, and it's so useful in a lot of ways. Organic compounds are usually what we smell. So anytime you smell something, it smells good, it smells bad. Generally, the smell you are smelling is some type of organic compound. So that's kind of neat. For example, isoamyl acetate is the smell that you smell when you smell bananas, right? And it looks like this. This is isoamyl acetate. And we'll talk about how to read these types of structures in a bit. It's the smell you smell when you think of bananas. Whereas cinnamaldehyde, which is the common name, not the IUPAC or International Naming System, is the smell in cinnamon. So when you smell cinnamon, you smell this guy. And so there are a lot of cool things aside from all the medical practices that organic chemistry has influenced. Pretty much any drug you've ever taken is probably an organic compound and required the study of organic chemistry. So why do we care about carbon? Well, like I said on the previous slide, life evolved based on carbon-containing compounds on Earth, at least. Because that organic chemistry is an incredibly important topic if you are interested at all in like microbiology or becoming a doctor or a veterinarian. Any type of study of life is going to have to know some knowledge of organic chemistry. Carbon contains 4 covalent bonds. This is kind of a big deal. It creates a large variety of different compounds that you can form because of the fact that it can bond to 4 things in total as a carbon center. In addition, it can form double and triple bonds, which is also kind of a big deal. It creates more diversity in the possible compounds that you can form, as well as their geometries in terms of their structures. For instance, like CO2, where we have a linear molecule, or CH2O, which is trigonal planar. Finally, another big deal is that carbon can catenate. And what that means is it, more than any other element, will bond to itself. This allows for the formation of long chains of carbon attached to carbon attached to carbon in compounds, as well as ring systems where carbon bonds to itself so many times that it forms a ring of carbon atoms, like these guys. That's a chain, at least. I got ring pictures later. So these are some big reasons as to why carbon's so special. Okay, so let's talk about the simplest type of carbon molecule out there, which is the hydrocarbon. This is the simplest type of organic compound. And it's simple because hydrocarbons, as the name kind of implies, are compounds that only contain 2 elements, hydrogen and carbon. These are the simplest type of organic compounds. We can separate hydrocarbons into 2 different groups. So they can be broken up into 2 different types of substances, and that's the aliphatic, the alkenes, which look like this, the alkanes, alkenes, which look like this, alkynes, which look like this, and the aromatic, which contain at least a benzene ring. I mean, this is my simplistic idea. You're going to learn a lot more about OChem if you have to take organic chemistry. If you have a benzene ring, like this part here, this is a benzene ring. It's aromatic for sure, but it also has to do with how the double bonds are spaced out, and you're going to learn a lot more about this in organic chemistry. Let's talk about the alkanes, alkenes, and alkynes. We're not going to focus on aromatic compounds. We're going to focus on aliphatic hydrocarbons. Alkanes have only single bonds around our carbon, as you can see here. Alkenes have at least one double bond. And alkynes have at least one triple bond somewhere in the compound. Doesn't matter where. Could be in the middle, could be at the end. If you have a triple bond anywhere in your hydrocarbon, it's an alkyne. If you have a double bond anywhere in your hydrocarbon, it's an alkene. And if you have no double bonds, only single bonds, it's an alkane. You can have more than one double bond, more than one triple bond, it's still an alkene or an alkyne, respectively. So, alkanes have carbon-carbon single bonds only. The generic formula is CnH2n plus 2. So in other words, if I have 3 carbons, H would be 3 times 2 plus 2, or in other words, 8. C3H8 would be that formula. Hey, that's propane. Or if we had 10 carbons, right, so we have C10, then we would have H22, because 2 times 10 plus 2 is 22. So here's ethane, which is C2H6. As you can see here, it still follows the same formula. We have 2 carbons, so that's the N. And 2 times 2 is 4, plus 2 is 6, and 1, 2, 3, 4, 5, 6 hydrogens. And there's the Lewis structure of it actually as well. Here's another one, right? This is again all single bonds. I don't know how many carbons this is. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 carbons here. So that would be 26 hydrogens, and if you count how many hydrogens there, should be 26. Like I said on the previous slide, alkenes have at least one carbon-carbon double bond. The generic formula is slightly different. If you have a single double bond present, then it's 2N for hydrogen. There's no plus 2 anymore, like there was in the alkanes. Anytime we add another double bond, we have to lose 2 more hydrogens in the structure. So if I have 2 double bonds, the formula would be CnH2n minus 2. Or if I have 1 triple bond, you'll see that that's the case as well. So if we look at this structure, this is ethene, and 2 carbons, we have 1 double bond, so 2N is how many hydrogens? 1, 2, 3, 4 hydrogens when we add 2 carbons. So you can kind of get the idea there, hopefully. If you have a question, just let me know. Same thing here. We have 1, 2, 3, 4, 4 carbons here and 1 double bond. So the formula should be CN2H2N. So 4 times 2N should be 8 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. So, all right. So let's look at alkynes. Alkynes have at least one carbon-carbon triple bond. They follow a generic formula of CnH2n minus 2. This is only for one triple bond. If you have more than one triple bond, you need to change that generic formula. But something like this, right? This is alkene, or ethene. We have 2 carbons. 2 times 2 is 4, minus 2 gives us 2 hydrogens, 1, 2. Or here we have butane. We have 4 carbons, 1, 2, 3, 4. And we have 1 triple bond, so 2N minus 2. So 4 times 2 is 8, minus 2 is 6. Hey, 3 hydrogens here, 3 hydrogens there. That's 6 total. All right. If you have any questions, just email me or come to office hours. All right, so there's a number of different ways to draw hydrocarbons, and as a thing, organic compounds like coordination compounds have structural isomers, like we learned about in that chapter covering coordination compounds. So there are very significant numbers of variations of organic compounds that actually have the same molecular formula, i.e. structural isomers. So same molecular formula, different compound due to the connections between atoms. Because organic molecules can be arranged in like thousands of different ways, how we draw the compound becomes very important for organic chemistry. So the most common way you guys have previously learned how to draw structures is through the use of Lewis structures, or otherwise known as structural formulas. These are just simply your regular old run-of-the-mill Lewis structure. In compounds, we're drawing bonds. Each line represents 2 electrons being shared in a covalent bond. If you have like elements that require lone pairs, you would draw those lone pairs around them. All that stuff we learned in Chem 1A applies here to structural formulas. However, we're going to learn some new ways of drawing organic compounds specifically. Another way of drawing them is known as a condensed structural formula. A lot of these, in my opinion, are just chemists getting lazy on our drawing. Less we have to draw, the better, in our opinion. So a condensed structural formula, these are the same exact molecule, just rotated a little bit here. You can see the double bonds here over here, but it's over there. So these are just flipped 180 degrees from each other. But the difference between them is in this one, we're not drawing the bonds to the hydrogen, but we're still drawing the hydrogen. We're writing the hydrogens in, right? So we have HC instead of line HC. And then we have CH2 here instead of showing the 2 H's attached to the carbon bonded there. So this is a shortcut. Another way of drawing them, and the biggest shortcut of them all, and honestly the most widely used way to draw organic molecules, is known as carbon skeleton formula or skeletal formula. And this is where chemists get as lazy as possible, in my opinion. And I'm using the same molecule for all of these. So here is butyne again. Butyne is 4-carbon atom molecule with a triple bond somewhere in it. This is specifically 1-butyne. And these two here have exactly the same orientation and everything. These are the same exact compound. These two, well, they all are, but this one, like I said earlier, is rotated from the others. In skeletal formula, we don't even draw the carbons. We don't even write C for carbon. We draw lines, and anytime a line ends or hits a kink, that's a carbon. So you can kind of see here, this ending line there is a carbon. This kink in the lines is a carbon. Where we form triple bonds, the stop of one line and the start of the 3 lines is a carbon, and where these 3 lines end is a carbon. So we have these 4 carbons in this structure, and that's supposed to be inherent knowledge about how we draw this. Now, we don't draw any hydrogens, and we don't even talk about the hydrogens really or show them at all in carbon skeleton formula. Now, what we do have to know about is that carbons like to have 4 bonds around them. So if our carbon doesn't have 4 bonds around it, then the remaining bonds are hydrogens bonded to it, right? So for instance, at this point here, you can kind of see we got 1 bond and 2 bonds around this carbon. There are 2 other bonds we're not showing, and they're attached to the hydrogen. Here, this carbon has 3 bonds right there attached to it. It's not showing its 4th. That 4th one is hydrogen. And the last one on here, this guy at that location actually has 4 bonds, so there are no hydrogens attached to that carbon. And this one has only 1 bond attached to it, so there are 3 hydrogens attached to it in reality. And these are just how we have to be able to read these structures and draw them. It's, again, probably the most widely used way to show structures in organic chemistry, so it's very important to get a handle on it rather quickly, especially for this class, as I will be using structure skeleton formula for a lot of the problems. Next is the next two forms of drawing structures are ball and stick model and space filling model. Both require a computer software, so we're not going to be using them. But just so that you can kind of see, again, this is the same as all that. The triple bond's right there. The software that we're running with both ball and stick model and space filling model, it costs about $1,500. So I'm not going to ask students to pay for that, obviously. I can't even afford that. So, but you can kind of see why it's beneficial. It has a three-dimensional image for it. It looks prettier for sure. Space filling model is actually as close as we can get to what the molecule would actually look like if we viewed it like under a super awesome microscope. So it's kind of the most correct or accurate way of showing a structure or a molecule. All right, so if you guys have any questions, as always, please let me know via email or in the discussion session.